Something is altering its path, and we might be its intended destination. 3. I-Atlas, an object from beyond our solar system, once believed to be merely a dormant cosmic traveler, has begun to subtly, yet consistently, increase its speed in a manner that defies conventional astronomical understanding. Independent analyses, drawing upon Avi Loeb's findings of non-gravitational acceleration near its closest approach to the Sun, indicate that if this outward push continues for just 50 days, its speed could increase by 86 meters per second. This change would be substantial enough to align its trajectory with our planet on December 19th, 2025. The critical questions are: is this a result of natural physics or some form of propulsion? Is it merely a confluence of dust particles interacting with sunlight, or a deliberate, guided movement? Coinciding with this unusual motion, a distinct radio frequency has been detected, 1.44 gigahertz. These faint rhythmic pulses, almost mathematical in their regularity, are echoing through the vast emptiness of space, hinting at a potential response. Could this signify a form of coordination? Continue with me, for by the conclusion of this presentation, you will grasp why many of the world's most astute scientific minds are now contemplating a truly astonishing possibility. 3. Atlas is not simply passing by. It may be actively steering towards us. If this developing enigma has captured your curiosity as profoundly as it has mine, please ensure you tap the like button and subscribe to our channel, so you remain fully informed of every update as this unfolding narrative progresses in real time. We encourage you to share your thoughts in the comments section, indicating your location, the current time there, and your perspective on this novel development. To further foster the growth of our community, we would be grateful if you shared this video across platforms such as X, Facebook, Reddit, or even within your private group conversations. Your support is what empowers us to continue pursuing such compelling stories. Therefore, thank you sincerely for having our support. Part 1. Unveiling the Assertion. A celestial entity is approaching. Currently, somewhere between the orbits of Mars and Jupiter, an object originating from another star system is traversing our solar neighborhood. This is not conjecture. It is not a work of fiction. The celestial body is an established reality. It has been assigned an official designation, 3E Atlas. Its discovery was made on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System, a crucial observatory located in Chile. What elevates this object to extraordinary status is not solely its origin from beyond our Sun's influence. What truly sets it apart is its current observed behavior. A series of pronouncements emerged on X, the prominent social media platform formerly known as Twitter. An independent researcher presented a calculation that commanded significant attention. The core assertion is as follows: should 3 Atlas maintain a non-gravitational acceleration of approximately 0.02 millimeters per second squared for a duration of roughly 50 days, it could achieve a change in its velocity amounting to about 86 meters per second. This calculated velocity alteration, according to the claim, would position the object to align with Earth's orbital path around December 19th, 2025. To reiterate, to align with Earth. The original post extended these claims further, proposing that this alignment was not accidental. It was framed as a deliberate act of course correction. Intriguingly, the pronouncement also referenced 1.44 gigahertz signals, suggesting alleged communication or possible trajectory adjustments, akin to a handshake between an extraterrestrial probe and a point within our vicinity, near Mars. Now, before you dismiss this presentation as just another unfounded conspiracy theory, let us consider the established facts. The object is verifiably real. Its orbital path is defined as hyperbolic, a clear indicator that it is not gravitationally bound to our Sun. It originated from interstellar space. Its perihelion, the point of closest approach to the Sun, occurred around October 30th, 2025. Furthermore, there are indeed documented observations of non-gravitational acceleration. This signifies that the object is exhibiting motion that cannot be explained by gravitational forces alone. Non-gravitational acceleration is not an inexplicable phenomenon. It is a manifestation of physical principles that we may not yet fully comprehend in this specific context. When a celestial body deviates from the trajectory predicted by gravity, an external force must be acting upon it. Typically, this external force is attributed to outgassing. Comets frequently exhibit this behavior. The sublimation of ice into vapor creates jets of gas that propel the object with a subtle yet measurable force. While 0.02 millimeters per second squared may seem minuscule, it is approximately 150,000th of Earth's gravitational pull. However, within the vacuum of space, over extended periods of days and weeks, these minute impulses can accumulate to produce a significant effect. Here is where the situation becomes particularly compelling. 3. Atlas represents only the third confirmed interstellar object ever detected. The first was Oumuamua in 2017, the enigmatic cigar-shaped entity that ignited extensive scientific debate. The second was Borisov in 2019, which presented as a conventional comet. Now we have 3 Atlas, and unlike its predecessors, this object is displaying behaviors that prompt profound and often unsettling questions. What are the potential implications? If this is simply a comet, albeit an unusual one, it remains a source of immense scientific value, offering a tangible sample from another star system passing through ours, providing crucial insights into planetary formation processes elsewhere in the galaxy. However, if the observed acceleration is indeed intentional, if some agency is actively steering this object, then we are confronting an event of an entirely different magnitude. We are contemplating the possibility, however remote, of an artificially constructed object originating from an alien civilization. The objective of this inquiry is straightforward. We will meticulously examine the assertion. We will scrutinize the available data, the underlying assumptions, the mathematical calculations, and the speculative leaps made. We will endeavor to differentiate between what is empirically known and what is currently being hypothesized. Furthermore, we will look ahead to the events anticipated in late 2025 and early 2026, a period during which observational data could either validate or definitively refute this hypothesis. This endeavor is not about fueling apprehension. It is about discerning objective reality, understanding potential scenarios, and separating signal from noise. The truth is that space is replete with phenomena that continue to elude our comprehension. Periodically, an object emerges that challenges our established scientific models. 3 Atlas might be such an object, or it might simply be a rare type of interstellar comet exhibiting outgassing in ways that appear unusual to us. By the conclusion of this presentation, you will be faced with a pivotal question. Is it a natural comet, an alien probe, or something in between? You will possess the necessary tools to form your own informed judgment. You will gain an understanding of the relevant scientific principles, the mathematical frameworks, the observational strategies, and the broader ramifications of this discovery. And you will be equipped to identify what to monitor in the coming months. The structure of this investigation will unfold in 3 distinct phases. Act 1 will focus on presenting the core assertion and the supporting data. We will examine the intrinsic nature of 3 Atlas, analyze the quantitative evidence, and identify the assumptions that underpin the proposed scenario involving an Earth intercept. Act 2 will delve into more speculative interpretations, addressing the controversies, contrasting natural explanations with more exotic possibilities, and exploring the narratives amplified across social media platforms. Act 3 will broaden our perspective to encompass recent advancements in space science, artificial intelligence, and radio astronomy, thereby contextualizing 3 Atlas within the vanguard of scientific discovery. We will then conclude with an outline of future developments and guidance on what aspects to observe. One final consideration before we proceed. The universe operates with a profound indifference to our comfort or readiness. For the majority of human history, our understanding of our place in the cosmos was limited. We believed ourselves to be unique, with Earth at the center of all existence, the focal point around which the entire universe revolved. Every significant scientific revelation since then has served to foster a greater sense of humility. We came to understand that Earth orbits the Sun. We learned that our Sun is but one among billions. We discovered that galaxies extend far beyond our ability to count. Now, we are learning that objects from distant star systems are capable of visiting our own. What is the consequence when one of these visitors exhibits behavior that defies our current understanding? In the subsequent section, we will closely examine the actual data to enable you to assess for yourself whether this claim withstands scrutiny or dissolves under examination. Part 2. A meticulous examination of the data. The discovery of 3 Atlas occurred on July 1st, 2025. The asteroid Terrestrial Impact Last Alert System, a network of telescopes situated in Chile and specifically designed for the detection of near-Earth objects, identified an anomaly. Initially, it presented as a faint point of light traversing the night sky. However, subsequent orbital calculations rapidly revealed its extraordinary nature. Its trajectory was classified as hyperbolic. A hyperbolic trajectory signifies that the object is not gravitationally tethered to our Sun. It is moving at a velocity too high to be captured by the Sun's gravitational pull. This implies it originated from an external source, passed through our solar system, and is now departing, heading back into the vast expanse between star systems. This characteristic is a definitive marker of an interstellar visitor. The object was subsequently assigned the designation 3, marking it as the third confirmed interstellar object ever detected. Let us now discuss its orbital parameters. Perihelion, its closest approach to the Sun, took place around October 30th, 2025. The distance at this point was approximately 1.36 to 1.4 astronomical units. Recall that 1 astronomical unit represents the average distance between Earth and the Sun, roughly 150 million kilometers. Therefore, at perihelion, 3 Atlas was situated at a distance of approximately 203 to 210 million kilometers from the Sun, placing it roughly within the orbit of Mars. Its predicted closest approach to Earth is scheduled for December 19th, 2025. At this juncture, the distance will be approximately 1.8 astronomical units, equating to roughly 268 to 270 million kilometers. To provide a sense of scale, the Moon is approximately 384,000 kilometers from Earth. This object will pass at a distance equivalent to approximately 700 times the Earth-Moon separation. This is an immense distance, far outside any conventional definition of a close encounter. Now we arrive at the perplexing anomaly. In a publication on the platform Medium, Avi Loeb, the distinguished Harvard astrophysicist renowned for his research on Oumuamua and his pursuit of extraterrestrial technology, reported an unusual observation. Astrometric data obtained from the Jet Propulsion Laboratory and the Atacama Large Millimeter Array revealed a deviation from the object's anticipated path. It was not positioned where it should have been if gravity were the sole influencing factor. This positional offset amounted to approximately 4 arcseconds, a minuscule angular shift, yet significant when tracking an object across millions of kilometers. Loeb's calculations yielded a non-gravitational acceleration value of approximately 0.02 millimeters per second squared. He subsequently employed a momentum conservation equation to investigate potential causes for this acceleration. If outgassing is the primary mechanism, meaning jets of vapor expelled from the object are generating thrust, then the rate of mass loss would need to be substantial. His analysis suggested that at least 1/16 of the object's total mass would have to sublimate over the course of approximately 1 month to account for the observed level of acceleration. Let us pause to consider this figure. While this rate of mass loss might seem unusual, it is not entirely unprecedented. Comets experience such phenomena routinely. When ice transitions directly from a solid to a gaseous state, a process known as sublimation, it escapes from the object's surface, generating a propulsive force. This is akin to a miniature rocket engine, weak but quantifiable. The challenge with 3 Atlas lies in the sheer scale of this potential mass loss. If the object possesses the substantial mass indicated by some estimates, potentially tens of billions of tons, then losing 1/16 of that mass within a single month should result in the emission of a spectacular cloud of gas and dust, a visible coma, and a prominent tail, phenomena that we would expect to readily detect. Visually, 3 Atlas has presented several intriguing characteristics. Imaging data has revealed a distinct jet structure, which appears to be directed towards the sun rather than away from it, an unusual orientation. The object's color has also drawn attention. Reports describe it as possessing a bluer hue than the sun, a potential indicator of ionized carbon monoxide rather than conventional dust particles. These are indeed clues, but they are not conclusive evidence. Comets, particularly interstellar comets, can exhibit a wide range of peculiar behaviors. What does the data definitively not show? Avi Loeb himself does not assert that the object is on a trajectory that will intercept Earth. He also does not claim that it is intentionally maneuvering towards our planet. The data unequivocally demonstrate an acceleration and a positional deviation. They strongly suggest that something anomalous is occurring. The extrapolation to an Earth intercept scenario and the inference of deliberate steering originates from other sources. It stems from social media posts that have taken Loeb's numerical findings and extrapolated them through further calculations. It is crucial to understand this key distinction. The raw data are intriguing but not inherently inexplicable. We are observing a hyperbolic interstellar object exhibiting some degree of outgassing and a jet structure that aligns with known physical principles. It is certainly on the unusual end of the spectrum, but not outside the realm of possibility. The fundamental question is whether the existing data genuinely support the bold claim that 3 Atlas is actively altering its course towards Earth, or whether real observational data have been overlaid with layers of assumption to arrive at a dramatic, sensational conclusion. As of now, the established facts are as follows. An interstellar object, confirmed and real. Its trajectory brings it relatively close to Earth, though still at a vast distance. A non-gravitational acceleration is present, which could be attributed to outgassing or potentially another cause, and a mathematical calculation demonstrating that a small, sustained propulsive force over a 50-day period could result in a significant alteration of velocity. Is this sufficient evidence to assert that the object is aligning with Earth? That is the question we will address in the subsequent segment by meticulously examining the mathematical underpinnings and the assumptions that transform raw data into a compelling narrative. Part 3. Extrapolation to Earth Intercept. The intersection of mathematics and assumptions. Let us commence with the arithmetic. The assertion circulating on social media begins with a fundamental equation from classical physics. Acceleration multiplied by time equals the change in velocity. If an object experiences a constant acceleration of 0.02 millimeters per second squared for a duration of 50 days, What is the resulting change in its velocity? 50 days equates to 4,320,000 seconds. Multiplying this by 0.02 millimeters per second squared, which is equivalent to 2 times 10 to the power of minus 5 meters per second squared, yields an approximate velocity change of 86.4 meters per second. This is the delta V, the magnitude of the velocity alteration. The mathematical calculation itself is accurate. There is no dispute regarding the fundamental arithmetic. Now, let us consider the displacement. When a constant acceleration is applied over a period of time, it not only alters velocity but also changes the object's position. The formula for displacement under constant acceleration is 1/2 multiplied by acceleration, multiplied by time squared. Plugging in the figures, 1/2 multiplied by 2 times 10 to the power of minus 5 meters per second squared, multiplied by 4.3, 2 times 10, to the power of 6 seconds squared, results in approximately 1.87 times 10 to the power of 8 meters. This is equivalent to 187,000 kilometers, which is roughly half the distance from Earth to the Moon. Thus, the numbers are indeed significant. A modest but continuous thrust applied over 50 days could indeed shift an object's path by hundreds of thousands of kilometers. In the context of orbital mechanics, this magnitude of alteration is substantial. It possesses the potential to modify an object's position when it crosses a particular orbital plane, to alter the closest approach distance, and theoretically, to transform a distant flyby into a considerably nearer encounter. However, this is precisely where assumptions begin to accumulate. This calculation presumes that the acceleration remains constant and unabated for the entire 50-day period. Is this assumption valid? We do not possess the data to confirm this. The acceleration was observed and measured at a specific point in time, near perihelion. Whether this rate of acceleration persists for weeks or months remains uncertain. Outgassing, a primary candidate for generating such acceleration, typically fluctuates in intensity based on the object's proximity to the Sun. As an object moves further away from perihelion, the solar heating diminishes, consequently reducing the rate of sublimation and thus the propulsive thrust. The acceleration might weaken or cease entirely. Furthermore, the calculation assumes that the acceleration is applied precisely along the optimal vector or direction. The direction of the applied force is as critical as its magnitude. If the thrust is directed laterally, perpendicular to Earth's orbital path, it might alter the orbital plane but would not significantly reduce the closest approach distance. If the thrust is applied in a prograde direction, increasing the object's speed, it would affect its arrival time. Conversely, a retrograde thrust, slowing the object down, would have a similar effect on timing. If the thrust is radial, pushing either towards or away from the Sun, it would alter the semi-major axis and eccentricity of the orbit. Without precise knowledge of the acceleration's direction, extrapolating the velocity change to predict a future trajectory is inherently speculative. Timing represents another critical assumption. For an intercept to occur, the object must apply its propulsive force at the precise moment and in the specific direction required to intersect Earth's orbit precisely when Earth is present at that intersection point. Earth traverses the solar system at an average speed of approximately 30 kilometers per second. It covers vast distances within a matter of days. Successfully targeting a moving celestial body necessitates exceptionally precise timing and directional control. While a displacement of 187,000 kilometers might indeed shift the point of orbital crossing, if Earth is not present at that specific location and moment, the intended intercept will not materialize. Then there is the question of energy expenditure and mass. If the object possesses the substantial mass suggested by some estimates, potentially tens of billions of tons, then sustaining a continuous thrust for an extended period would demand an immense energy source. If the thrust is derived from natural outgassing, the rate of mass loss must be considerable, as calculated by Loeb. If, however, the propulsion is artificial, it implies the existence of a system capable of generating long-duration thrust. Both of these scenarios strain credulity unless supported by corroborating evidence. Finally, we must account for the influence of gravitational perturbations. Space is not an entirely empty medium. Factors such as solar radiation pressure, the gravitational pull of other planets, the solar wind, and even the Yarkovsky effect can all subtly influence the trajectory of smaller celestial bodies. The simplified calculation operates under the assumption that these external influences are negligible or effectively cancel each other out over time. In reality, however, they introduce variability and uncertainty into trajectory predictions. A purely deterministic 50-day thrust represents an idealized scenario. Allow me to offer an analogy. Imagine you are driving on a highway and you know you can increase your speed by 60 kilometers per hour. This is akin to knowing your potential delta V. However, to successfully merge into the correct lane at the opportune moment to reach a specific exit requires more than just raw speed. You need to know the precise location of the exit, the prevailing traffic speed, the optimal moment to accelerate, and the precise angle at which to steer. The arithmetic of velocity change is one aspect of the equation. The geometry and timing involved in orbital mechanics represent an entirely different set of considerations. The extrapolation presented on social media assumes that the observed acceleration was directed in a manner conducive to an Earth intercept. We lack concrete evidence to support this assumption. While the data confirms some level of acceleration, they do not specify its vector relative to Earth's orbital path. The assertion then adds, this acceleration is purposeful and Earth-targeting. This is an interpretation layered upon the existing data, not an intrinsic derivation from it. Here is a summary of what we definitively know versus what remains assumed. We know that a non-gravitational acceleration is occurring. We know it is subtle but measurable. We know the object's current orbital path brings it into Earth's general vicinity in December. We assume that this acceleration will persist for 50 days. We assume that it is directed precisely in the necessary direction. We assume that the timing of its application will align perfectly with Earth's position. We assume that no other significant factors will interfere with this process, and we interpret all of these assumptions as evidence of intentional maneuvering towards Earth. Each assumption functions as a link in a chain of reasoning. If even one of these links is broken, the entire claim loses its foundational support. The crucial question is not whether the mathematical calculations are correct. They are. The pivotal question is whether the complex realities of the cosmos conform to these simplifying assumptions. In the next section, we will examine the actual trajectory and the calculated closest approach distance to ascertain whether a velocity change of 86 meters per second could realistically transform a distant flyby into something far more concerning. Part 4. The object's trajectory and closest approach. The official figures provided by NASA and the European Space Agency are unequivocal. According to their data, 3E Atlas is projected to pass Earth at a distance of approximately 1.88 astronomical units on December 19, 2025. This translates to a separation of roughly 268 to 270 million kilometers. To contextualize this immense distance, one astronomical unit represents the average distance between Earth and the Sun, approximately 150 million kilometers. Therefore, at its closest approach, the object will be nearly double the Earth's own orbital radius from the Sun. This is unequivocally not a close encounter. By any standard employed in the field of planetary defense, this object poses no immediate threat. An object is classified as potentially hazardous if its orbital path brings it within 0.05 astronomical units of Earth, a distance of approximately 7.5 million kilometers. 3E Atlas will pass at a distance exceeding 30 times this threshold. Both NASA and the European Space Agency have explicitly stated that the object presents no danger to our planet. Therefore, how are closest approach distances calculated in orbital mechanics? When an object approaches on a hyperbolic trajectory, its path is primarily determined by its velocity, its direction of travel, and the cumulative gravitational influences it encounters. The closest approach distance is essentially the minimum separation point calculated based on the object's predicted trajectory relative to Earth's position at a specific moment in time. For 3 Atlas, this calculation definitively yields a distance of 1.8 astronomical units on December 19th. Now, let us address the central inquiry. Could a velocity change of 86 meters per second significantly alter this calculated closest approach distance? The answer is both yes and no, depending entirely on the context. Yes, in principle, a delta V of 86 meters per second applied over a 50-day period could indeed shift an object's trajectory by hundreds of thousands of kilometers. As we previously calculated, the potential displacement could be in the vicinity of 187,000 kilometers. This is not an insignificant distance. In the realm of orbital mechanics, even minor alterations in velocity can lead to substantial changes in position over extended periods, particularly if applied early in an object's trajectory. However, the answer is also no, because converting a projected miss distance of 270 million kilometers into a direct Earth impact would necessitate a far greater delta 5, unless the direction and timing of any applied thrust were extraordinarily favorable. The object is currently traveling at a velocity of approximately 60 kilometers per second, or 60,000 meters per second. The proposed velocity change of 86 meters per second represents less than 0.15% of its total orbital speed. To alter the trajectory sufficiently to reduce the missed distance from 270 million kilometers to zero would require either a substantially larger delta V or an almost perfect alignment of the thrust vector and its timing. The direction of any applied thrust is paramount. Imagine the object's trajectory as a line segment in three-dimensional space. If a force is applied perpendicularly to the velocity vector, this is known as a sideways thrust, and it primarily alters the orbital plane. This could result in a lateral shift of perhaps 100,000 kilometers, but it would not necessarily bring the object any closer to Earth. If the thrust is applied either forward or backward along the direction of motion, this modifies the object's speed and consequently its arrival time. If the thrust is radial, pushing either towards or away from the Sun, it directly influences the object's orbital path, affecting its semi-major axis and eccentricity. The direction of the applied force is the most critical factor. Without precise knowledge of the acceleration's vector relative to Earth's orbit, integrating the velocity change into a predictive trajectory model becomes highly speculative. The celestial body might arrive within the Sun's equatorial plane at an earlier or later juncture, yet this temporal arrival does not ensure a closer proximity unless Earth coincidentally occupies that precise spatial coordinate. Any propulsive force exerted radially, either towards or away from the Sun, serves to modify the orbit's configuration, its eccentricity, and the closest approach distance. Orbital mechanics incorporates a conceptual framework known as the B-plane. This is an imaginary surface oriented perpendicular to the object's inbound path, employed to ascertain its intersection point relative to a designated target. Imagine this construct akin to a target used in archery. Earth represents the bullseye. The trajectory of the celestial body pierces this plane at a certain location, and the distance from the bullseye to this piercing point quantifies the deviation. A minute alteration in velocity can shift the plane's intersection point, but transitioning from the periphery of the target to its center necessitates a precisely calibrated impetus. Absent a clear understanding of the direction of 3I Atlas's non-gravitational acceleration relative to Earth's current position, it is impossible to quantify the actual change in the missed distance. The assertions circulating on social media presume that any applied force is directed optimally, a significant assumption indeed. Furthermore, the object's mass is a pertinent consideration. Current estimations suggest that 3 Atlas possesses considerable mass, potentially exceeding 33 billion tons, with a diameter spanning several kilometers. Manipulating an entity of such magnitude via natural outgassing presents a considerable challenge. It is akin to attempting to guide a mountain by vaporizing ice from its surface. Should the driving mechanism be artificial, it would imply the presence of an engine or propulsion system of immense power. In either scenario, the underlying physics presents formidable difficulties. Scientists at NASA and the ISA, who have access to complete astrometric data and sophisticated orbital models, have concluded that the object is not on a collision course with Earth. Their analyses incorporate factors of uncertainty, gravitational perturbations, and potential non-gravitational forces. Their simulations project a safe transit. Were the data to indicate otherwise, even a minor probability of impact, it would trigger immediate alarms. Planetary defense systems are specifically established to detect and monitor potentially hazardous celestial bodies. 3 Atlas is not currently categorized as such. Therefore, a pragmatic assessment of the missed-distance reality boils down to this. The confluence of geometric alignment and temporal phasing renders an Earth impact scenario highly improbable at this juncture. The object would require a considerably more substantial velocity modification applied in a very precise direction and at a very specific moment to transform a trajectory that passes 270 million kilometers distant into a perilous encounter. While the numerical values might appear alarming when focusing solely on the arithmetic of velocity change, delta v, a comprehensive examination encompassing orbital mechanics, timing, and missed distance collectively points towards a distant passage. This does not diminish the object's intrinsic scientific interest, quite the opposite. Its non-gravitational acceleration, its unusual characteristics, and its very nature as an interstellar visitor imbue it with significant scientific value. However, the notion of an Earth intercept scenario, the assertion that it is aligning with our planet, remains speculative. Subsequently, we will delve into the intensifying observational campaign currently underway, the array of telescopes focused on 3I Atlas, and the verifiable predictions that will soon elucidate whether this object is a comet, a probe, or something situated between these classifications. Part 5. Observational Campaign and Testable Predictions. The forthcoming months are pivotal. Between the present moment and early 2026, 3I Atlas will be subjected to rigorous scrutiny. Telescopes situated across the globe, as well as those in orbit, are already tracking its path. The closest approach to the Sun, perihelion passage, occurred around October 30th, 2025, at which point the object reached its minimum distance from the Sun. It is now receding, charting a course towards its close approach with Earth on December 19th. This period represents the optimal observation window, a transient opportunity. Once the object recedes beyond Earth and ventures deeper into the outer solar system, its visibility will diminish. The principal instruments participating in this campaign encompass some of humanity's most advanced technological creations. The Hubble Space Telescope is capable of capturing high-resolution imagery across visible and ultraviolet spectra. The James Webb Space Telescope, equipped with its infrared sensing capabilities, can detect thermal signatures and analyze the chemical composition of any gaseous or particulate matter surrounding the object. Terrestrial observatories, such as the Very Large Telescope situated in Chile and the KEK Observatory in Hawaii, are also contributing to the effort. Radio telescopes are actively engaged in detecting any anomalous emissions. Furthermore, from our terrestrial vantage point, Mars orbiters may potentially capture fleeting glimpses as 3I Atlas traverses relatively close to the red planet. An intriguing temporal coincidence also presents itself. On November 4, 2025, the European Space Agency's Jupiter Icy Moons Explorer, designated as JUICE, will pass within an approximate distance of 64 million kilometers of 3I Atlas. While not close enough for a dedicated close-approach maneuver, JUICE's instruments may be able to acquire data from this considerable separation. Every fragment of information acquired contributes to the overall understanding. Avi and his research colleagues have formulated a series of empirical predictions. These predictions are contingent upon whether the observed non-gravitational acceleration stems from natural outgassing or an alternative source. If outgassing is the causal factor, the resultant mass loss ought to be substantial. Lowe's calculations indicated that at least 1/16 of the object's mass would sublimate over approximately a 1-month period. This phenomenon should manifest as a considerable cloud of gas and dust, a discernible coma, and likely a tail extending rearward, propelled by the solar wind. Consequently, the initial prediction is quite straightforward. If the acceleration is indeed a natural phenomenon, telescopic observations should reveal a substantial envelope of gas and dust. Spectroscopic analysis should confirm the presence of volatile compounds, such as water, carbon monoxide, carbon dioxide, or methane. The object should exhibit behaviors consistent with those of a comet, displaying all the characteristic signs of activity driven by sublimation. Conversely, if no expansive cloud is detected and the mass loss is minimal or absent, the hypothesis of natural outgassing is significantly weakened. This outcome would represent a notable scientific finding, suggesting that the acceleration originates from a different source, one that does not necessitate the expulsion of substantial material. In such a case, non-natural or technologically derived explanations would gain increased plausibility. Key measurements to monitor include astrometric residuals, which represent the discrepancies between the object's actual position and its predicted location based solely on gravitational forces. These residuals provide insight into the magnitude and direction of any non-gravitational influences. Over the ensuing weeks, as more observational data accumulates, astronomers will refine the orbital calculations and quantify the acceleration with enhanced precision. Spectroscopy serves as another critical analytical tool. By dissecting the light emitted by the object into its constituent wavelengths, scientists can identify the specific molecules and atoms present. 3 Atlas has already garnered attention for its unusual coloration, described as exhibiting a bluer hue than the sun. This could be indicative of ionized carbon monoxide, a molecular signature associated with certain types of comets, or it might signify something entirely different. Detailed spectroscopic analysis will offer greater clarity regarding its composition and its concordance with established cometary chemistry. Imaging is also of considerable importance. The morphology of any observed coma or tail, the structure of any emanating jets, and the presence of asymmetries all provide valuable clues. Some reports have alluded to an anti-tail, a jet directed towards the sun rather than away from it. While unusual, this phenomenon is not unprecedented. Comets occasionally display features oriented forward due to observational geometry or rotational effects. High-resolution imagery will serve to ascertain whether these observed phenomena are consistent with natural processes. Additionally, Radio astronomy plays a role. Social media commentaries have asserted that the object was transmitting signals at 1.4 gigahertz, purportedly communications or course correction signals. This claim remains entirely unverified, yet radio telescopes will nonetheless be listening for any such emanations. Should any anomalous emissions be detected, whether at 1.4 gigahertz or any other frequency, they will be captured and subjected to analysis. While radio signals from a comet are infrequent, they are not impossible, typically being associated with plasma interactions. However, a powerful and structured signal would represent a profoundly different scenario. The observational campaign faces its own set of challenges. Temporal and geometric factors are particularly critical around perihelion. During this phase, the object was situated close to the sun in the sky, making observation difficult due to the overwhelming solar glare. As it recedes from the sun and approaches Earth, its visibility improves. However, by late December, following its close approach, it will begin to fade as it moves further from both the sun and Earth. The observational window is thus constrained. Environmental conditions, telescope availability, funding, and interagency coordination all exert influence. Not all telescopes are capable of observing every night. The subsequent reduction and analysis of data, along with peer review and publication, require significant time. Scientific progress proceeds at a pace considerably slower than that of social media dissemination. Claims may propagate within hours, but the process of observation and confirmation or refutation spans weeks or months. Nevertheless, this is an exceptionally exciting period. We are witnessing a visitor from another star system in real time. The very same telescopes that probe distant exoplanets and investigate the atmospheric composition of alien worlds are now focused on an object traversing our own cosmic neighborhood. This represents a rare convergence of opportunity and technological capability. By early 2026, we anticipate having definitive answers. If 3 Atlas behaves in a manner consistent with a comet, exhibiting substantial outgassing, a coma, a tail, and spectroscopic signatures indicative of volatile compounds, then the natural explanation will prevail. The non-gravitational acceleration will be attributed to a comet engaged in typical cometary activity, perhaps amplified by its interstellar origin and composition. However, should the observational results reveal minimal mass loss, no significant cloud formation, and yet the acceleration persists or exhibits directional properties inconsistent with jetting, then we encounter a significant scientific conundrum. This would not constitute a disaster, but rather a perplexing puzzle that defies easy categorization within our current models. At that juncture, the discourse will shift. At that point, the more speculative hypotheses, which we will explore in the subsequent discussion, will transition from idle conjecture to subjects demanding serious scientific consideration. The subsequent phase of this investigation will address the debate between natural and non-natural explanations, the influence of social media in amplifying unsubstantiated claims, and the implications should 3 Atlas prove to be something other than a comet. Part 6. Non-gravitational acceleration, natural explanations. Comets are commonly described as celestial bodies composed of ice and dust, often simplified as dirty snowballs in introductory astronomy. The nucleus of a comet is a composite mixture of frozen volatiles, rocky material, and organic compounds. As a comet approaches the sun, solar radiation heats its surface, causing these ices to sublimate, transitioning directly from a solid state to a gaseous phase without passing through a liquid intermediate. The escaping gases carry entrained dust particles, forming an enveloping cloud known as a coma, and frequently a tail that trails away from the sun. This outgassing process not only generates a visually striking spectacle, but also imparts a propulsive force. The molecules of gas carry momentum. As they are expelled from the nucleus, they exert a recoil force on the comet itself, analogous to a leaky balloon propelling itself erratically across a room. While the effect is subtle, it is measurable and is termed a non-gravitational force. Astronomers have been detecting and modeling this phenomenon for many decades. Therefore, when Avi reports a non-gravitational acceleration of 0.02 millimeters per second squared for 3I Atlas, the initial scientific assumption is that this acceleration is caused by outgassing. This represents the default hypothesis, the most parsimonious explanation. However, the precise details are critically important. Lowe employed a momentum conservation equation to estimate the requisite mass loss to generate such an acceleration. The underlying formula is straightforward. The force exerted on the comet is equivalent to the rate of mass loss multiplied by the velocity of the escaping gas. Since force equals mass times acceleration, one can rearrange the equation to solve for the mass loss rate. Given an outflow velocity of a few hundred meters per second, typical for cometary jets, and an acceleration of 0.02 millimeters per second squared, it is possible to calculate the rate at which the comet is losing mass. The result is quite striking. If 3 Atlas possesses a mass of approximately 30 billion tons, the calculation suggests that it would need to shed roughly 5 billion tons per month to sustain this level of acceleration. This equates to approximately 1/16 of its total mass being lost within a 30-day period. Over the span of several months, the comet would effectively evaporate a substantial portion of its own substance. This magnitude of mass loss should be readily observable. Astronomers would anticipate the detection of a colossal coma, an extensive cloud of gas and dust enveloping the nucleus. The tail should be prominent, and spectroscopic analysis should reveal abundant volatile compounds. Yet, thus far, observational data indicates a more subdued phenomenon. Reports mention a jet directed towards the sun, and the object's color deviates from expectations, appearing bluer than usual. However, a substantial coma commensurate with the predicted mass loss rate has not yet been definitively observed. This observation does not definitively invalidate the natural explanation. Comets exhibit variable behavior. Outgassing can occur episodically, influenced by the object's rotation, the exposure of freshly sublimated ices, or the collapse of surface layers. It is conceivable that the high mass loss rate was a transient event, a burst of activity near perihelion that has since diminished. Alternatively, the gas might be escaping through a focused jet rather than dispersing uniformly, rendering the coma less conspicuous from Earth. It is also possible that the composition of the ejected material is such that the gas is highly transparent or carries minimal dust, thereby reducing its visibility. The coloration, described as bluer than the sun, is particularly intriguing. It might signify the presence of ionized carbon monoxide, a molecule that can dominate the spectral signature of certain comets. Carbon monoxide ice is more volatile than water ice, sublimating at lower temperatures and at greater distances from the sun. An interstellar comet, having formed in a different stellar environment, could possess a distinct composition, potentially richer in carbon monoxide or other exotic ices compared to comets originating within our solar system. Certain images depict what might be an anti-tail, a feature oriented towards the sun rather than away from it. This is an uncommon but not impossible occurrence. It can arise from the specific geometric perspective of the observer, where the dust within the orbital plane appears to point forward. Alternatively, it could represent a genuine forward-directed jet, driven by the object's rotation or localized heating events. The natural explanation necessitates the cohesive integration of all these disparate elements: substantial mass loss, unusual composition, episodic outgassing, and geometric observational effects. It presents a complex scenario, but comets themselves are intrinsically complex entities, exhibiting diverse behaviors. An interstellar comet, formed in another stellar system under different conditions, could readily diverge from the patterns observed in solar system comets. The object's estimated size and mass also warrant consideration. Projections indicate a diameter of at least several kilometers, possibly exceeding 5, and a mass surpassing 30 billion tons. This represents a colossal comet. To accelerate a body of such immense mass through outgassing requires prodigious amounts of energy and material expulsion. It is analogous to attempting to propel a massive cargo ship by jettisoning its cargo. While achievable, it demands the rapid ejection of substantial quantities of material. Analogies can be helpful here. Envision a gargantuan container vessel losing half its cargo over a month to achieve a minor increase in speed. This is conceivable but would be a dramatic event, accompanied by the expectation of widespread debris. Similarly, if 3 Atlas is losing 1/16th of its mass within a month, evidence of this loss, such as gas, dust, or a luminous envelope, should be apparent. What would constitute a satisfactory confirmation of the natural explanation? It would involve the detection of a large coma consistent with the predicted mass loss rate. Spectroscopic analysis should confirm the presence of water, carbon monoxide, carbon dioxide, or other volatiles in quantities that align with expectations. Imaging should reveal a classic cometary structure, possibly including a tail and multiple jets. Most crucially, the acceleration should demonstrate a correlation with the object's distance from the Sun. As the comet's exposure to solar heating diminishes, outgassing should weaken, and the acceleration should consequently decrease. If, however, the acceleration persists or even intensifies as the comet moves further from the Sun, this would represent a significant red flag. Presently, the hypothesis of natural outgassing remains plausible, albeit demanding. The estimated mass loss rate is exceptionally high, and the observational evidence is not definitively conclusive. The object's considerable size and mass further complicate the narrative. Nevertheless, comets have surprised us in the past. Oumuamua astonished us with its acceleration and elongated form. Borisov presented a surprisingly typical cometary appearance. 3I Atlas might simply be the next such surprise, a comet exhibiting extreme characteristics that push the boundaries of our established understanding of typical cometary behavior. Alternatively, it could represent something entirely different. This leads us to the next area of exploration, the speculative yet scientifically intriguing technological hypotheses. Part 7. Non-gravitational acceleration, exotic technological hypotheses. What if the observed acceleration is not a product of natural processes? What if 3 Atlas is not merely a comet behaving in a typical manner? What if it is an artifact, something deliberately constructed and dispatched? What if it is designed? Avi and his colleagues have authored a scientific paper titled, "Is the Interstellar Object 3 Atlas Alien Technology?" This inquiry is not presented facetiously, but rather as a serious scientific investigation, framed within the constraints of what can be scientifically validated or refuted. The paper contemplates the possibility that the object is a technological construct, perhaps a probe dispatched by an extraterrestrial civilization. Several factors converge to prompt this consideration. Firstly, the non-gravitational acceleration itself. If it cannot be adequately explained by outgassing, or if the outgassing explanation strains credulity due to the excessive mass loss rate required, then alternative mechanisms must be considered. Secondly, the estimated size and mass of the object. A large, massive entity exhibiting measurable acceleration implies a significant transfer of energy and momentum. Thirdly, its trajectory. Lowe has noted that the object's path through the inner solar system, its temporal sequencing, and its alignment with Earth's orbital plane present statistically unusual characteristics. While not mathematically impossible, these factors are improbable for a purely random interstellar visitor. The energetic requirements warrant detailed examination. For an object with a mass measured in tens of billions of tons to sustain an acceleration of 0.02 millimeters per second squared over a period of weeks necessitates a substantial propulsive force. Force equals mass multiplied by acceleration. Substituting values of 10 to the power of 13 kilograms and 2 times 10 to the power of minus 5 meters per second squared yields a force of approximately 200,000 newtons. This is equivalent to the thrust generated by a relatively small rocket engine, maintained continuously to achieve sustained acceleration. However, the efficiency of solar sails is limited unless they are exceptionally large and highly reflective. Calculations suggest that a sail of sufficient size to accelerate this mass would need to span kilometers and be precisely oriented. Alternatively, more exotic propulsion systems might be involved, such as ion drives, fusion engines, or technologies yet to be conceived. The mention of 1.4 gigahertz pings in social media reports adds another dimension to this hypothesis. The frequency of 1.4 gigahertz holds particular significance in the search for extraterrestrial intelligence, as it corresponds to the hydrogen line, a natural emission frequency from neutral hydrogen atoms. This frequency is sometimes referred to as the water hole in radio astronomy, representing a relatively quiet band within the electromagnetic spectrum, conducive to signal propagation across vast cosmic distances with minimal interference. If an advanced civilization were to transmit a signal, 1.4 gigahertz would logically be a preferred choice. However, a critical issue arises. There is no publicly verified detection of such pings originating from 3 Atlas. Radio telescopes continuously monitor the celestial sphere, and any strong, structured signal emanating from the object would likely have been detected by now. Thus, the claim remains unsubstantiated, residing in the realm of speculation. Nevertheless, let us entertain the hypothesis. Assuming 3 Atlas is an artificial probe, what would be its purpose? Reconnaissance or observation seem plausible objectives. It might have been passively drifting through space for millions of years, a remnant of a long-vanished civilization, still fulfilling its programmed mission to survey star systems. Alternatively, it could be an active entity, deliberately altering its course to investigate targets of interest. Could it intentionally maneuver to intercept Earth? In principle, the answer is yes, provided it possesses the requisite capabilities. A probe equipped with a functional propulsion system could, in theory, modify its trajectory. However, the delta V required to transform a 270 million kilometer miss distance into an actual intercept trajectory far exceeds 86 meters per second. Velocity changes on the order of kilometers per second, applied with precise timing and direction, would be necessary. This implies a substantial and sustained thrust over an extended period. Lowe has also discussed the dark forest hypothesis in the context of 3 Atlas. This concept, popularized by the science fiction author Liu Cixin, posits that the universe is teeming with civilizations, yet they remain silent to avoid detection by potentially hostile neighbors. Revealing one's presence could invite destruction, thus prompting all entities to conceal themselves within the cosmic dark forest. Lowe speculates that if 3 Atlas is a probe, its behavior might indicate a cautious strategy, observing from a distance rather than initiating direct engagement. This is purely hypothetical. Numerous assumptions are layered upon each other. The first assumption is that the acceleration observed is not natural. The second is that it is artificial. The third is that it is under the control of an intelligence. The fourth is that this intelligence exhibits caution or specific intent in its approach towards Earth. Each subsequent assumption diminishes the likelihood of the overall scenario. What would constitute definitive proof of a technological origin? Several possibilities come to mind. Unexpected radio transmissions, particularly structured signals carrying informational content. propulsion signatures that do not diminish over time, meaning sustained acceleration without a corresponding loss of mass or emission of gas. Extremely minimal mass loss coupled with significant acceleration, which would defy the principles of rocket propulsion unless an external energy source is involved. Highly reflective surfaces, suggesting the presence of manufactured materials rather than naturally occurring rock and ice. Alterations in orientation or position that cannot be attributed to uncontrolled rotation. Should observations reveal any of these phenomena, the conversation would shift dramatically. The extraordinary hypothesis would cease to be fringe speculation and become a credible explanation requiring thorough investigation. However, if none of these indicators emerge and the object continues to behave like an unusual but natural comet, then the technological hypothesis would recede into the background. The implications are profound. If the probe scenario is accurate, it would definitively prove our solitude is an illusion. It would signify that another civilization has achieved a technological level sufficient to dispatch objects across interstellar distances. This would prompt crucial questions about their motivations, their longevity, and their ultimate fate. Are they still active? Did they dispatch a single probe or 1,000? Is 3 Atlas an ancient artifact or a recent creation? Nevertheless, the magnitude of the stakes does not validate the hypothesis. Exceptional claims necessitate exceptional evidence. At present, the evidence is, at best, inconclusive. The observed non-gravitational acceleration is a verified phenomenon, but its origin is not definitively proven to be unnatural. The trajectory is unconventional, yet not impossible for a random interstellar object. The reported radio signals remain unconfirmed. The absence of a substantial coma is suggestive, but not definitive. Scientific methodology relies on rigorously testing hypotheses, formulating predictions, and validating them against observational data. The technological hypothesis also yields predictions. The absence of a large gaseous cloud due to a lack of outgassing. The continuation of acceleration, even as the object recedes from the Sun, indicating that its propulsion is independent of solar influence. The potential detection of radio emissions or other non-thermal signatures. Over the ensuing months, observations will serve to test these predictions. If the object proves to be a natural phenomenon, we will still have gained valuable knowledge. We will have expanded the frontiers of cometary science, explored the chemistry and dynamics of interstellar visitors, and rigorously tested our theoretical models against an extreme case. Should the object be determined to be artificial, that would represent the most significant discovery in human history. Regardless of the outcome, the observations expected in late 2025 and early 2026 will be captivating. Our next focus will be on how this narrative evolved, specifically how social media transformed scientific data into a story of alien interception and conspiracy. Part 8. The social media narrative and conspiratorial framing. The initial posts surfaced on X in mid-October 2025. An independent researcher, unaffiliated with any prominent institution, presented a series of assertions. The central claim was straightforward. 3 Atlas is accelerating. If it maintains an acceleration of 0.02 millimeters per second squared for 50 days, it will achieve a velocity increase of 86 meters per second. A velocity change of this magnitude, if applied in the correct direction at the appropriate time, could align the object with Earth's trajectory on December 19, 2025. Subsequently, the claims became more elaborate. The researcher posited that the acceleration was not random, but intentional. The object was actively maneuvering, correcting its course, and aiming towards Earth. There were also reports of 1.4 gigahertz pings detected in proximity to Mars, purported communications, and a form of handshake between the object and an unknown entity. The narrative transformed from an intriguing scientific anomaly into a scenario of an alien probe targeting us. Let us dissect this piece by piece. The data, specifically the information regarding acceleration, is accurate. A Vive reported this, and it is substantiated by astrometric observations from credible sources. The mathematical calculation that 0.02 millimeters per second squared multiplied by 50 days equals 86 meters per second is also correct. It adheres to fundamental physics principles. There are no errors in this calculation. However, the subsequent assumptions introduce uncertainty. The assumption that the acceleration will persist for precisely 50 days. The assumption that its direction is towards Earth. The assumption that the timing will perfectly coincide with Earth's orbital position. None of these assumptions have been verified. They represent extrapolations, educated guesses based on limited data. The interpretation, the assertion that the object is aligning itself with Earth, marks the point where data ends and narrative begins. Alignment implies intent. It suggests the object is deliberately navigating itself towards our planet. There is no evidence to support this claim. The estimated closest approach remains 270 million kilometers. NASA has stated there is no threat. The geometrical configuration does not support an intercept scenario unless multiple improbable factors converge. The 1.4 gigahertz pings are unconfirmed. No major observatory has corroborated radio emissions originating from 3 Atlas. If such a signal were indeed detected, radio astronomers would undoubtedly be investigating it intensely. The lack of confirmation does not definitively prove the pings did not occur, but it necessitates treating them with skepticism in the absence of supporting evidence. So, how did this narrative gain traction? Social media thrives on uncertainty and dramatic storytelling. A scientific anomaly, a gap in our understanding, becomes fertile ground for conjecture. Individuals take existing data, apply their own interpretations, and construct narratives. These narratives disseminate more rapidly than the scientific explanations because they are inherently more captivating. An alien probe targeting Earth generates far more excitement than a comet exhibiting unusual outgassing. The underlying psychology is fascinating. Humans possess an innate tendency to seek patterns. We perceive connections where none may exist. We are drawn to narratives that imbue chaos with meaning. An interstellar object exhibiting unexplained acceleration is not merely a comet behaving erratically. It is a sign, a message, perhaps even a warning. This claim resonates with broader societal anxieties concerning the unknown, the vastness of space, and our preparedness for potential extraterrestrial contact. Conspiratorial framing intensifies this phenomenon. Once the notion is introduced that the object might be artificial, every ambiguity is construed as evidence. The absence of a visible coma becomes proof it is not a comet. Its unusual coloration suggests engineered materials. Its trajectory implies deliberate targeting. The lack of official confirmation of the radio pings is interpreted as a cover-up. Consequently, the narrative becomes self-sustaining and resistant to contradictory information. This pattern is not unique to 3 Atlas. Objects like Oumuamua have undergone a similar cycle. A peculiar object appears, scientists admit their limited understanding, and the internet fills the void with alien explanations. Occasionally, scientists themselves, like Lowe, embrace speculation. Lowe is known for publicly entertaining exotic hypotheses, advocating for the consideration of all possibilities, including technological origins. While such openness is beneficial to scientific inquiry, it also provides fodder for sensationalism. Mainstream media outlets frequently amplify these stories, often in simplified or exaggerated forms. Headlines proclaim alien probes even when the accompanying article offers a more nuanced perspective. The New York Post published a piece quoting Lowe concerning 3 Atlas, framing it as a potential alien propulsion system. This framing is significant. The majority of readers do not progress beyond the headline. They absorb the idea that scientists believe it might be extraterrestrial in origin, and that becomes the prevailing narrative. The responsibility in scientific communication lies in clearly distinguishing between factual data and speculative extrapolation. The data confirms a non-gravitational acceleration, and that is the factual extent of it. The extrapolation to an Earth intercept, intentional maneuvering, and alien technology represents layered interpretations. While these interpretations might be accurate, they are not established facts. A careful balance must be struck. On one hand, we should avoid prematurely dismissing possibilities. Scientific progress often involves exploring ideas that initially appear improbable. On the other hand, speculation should not be equated with evidence. The assertion that 3 Atlas is aligning with Earth does not carry the same weight as the observation of its non-gravitational acceleration. One is a measured quantity, the other is an inference. Social media erodes this crucial distinction. Everything is presented as a claim, a theory, a possibility. The signal-to-noise ratio deteriorates, leading to debates about whether the object poses a threat without consensus on the actual data. Misinformation spreads not out of deliberate deception, but because the boundary between data and interpretation becomes blurred. This leads to a broader, meta-question. Are we equipped to handle these possibilities? What if the object is natural yet genuinely anomalous, pushing the boundaries of cometary physics? What if it is artificial, confirming we are not alone? How do we, as a society, process information in an environment where truth and speculation coexist seamlessly on the same platform? The social media discourse surrounding 3 Atlas serves as a case study in the intersection of science and narrative. The subsequent section will examine what transpires if the narrative evolves into something more substantial, if the object actually performs an unexpected action. Part 9. Worst Case Hypothesis. Intersection. Let us engage in a hypothetical exercise. This is scenario analysis, not a prediction. What if all the assumptions were valid? What if 3 Atlas somehow altered its trajectory sufficiently to intersect with Earth? What would be the implications? Firstly, the parameters. Estimates for the size of 3 Atlas range from several hundred meters to several kilometers in diameter. Some calculations based on its brightness and assumed albedo suggest it could be 5 kilometers across or even larger. Mass estimates exceed 30 billion tons, possibly more. This represents a colossal mass hurtling through space. Interstellar objects travel at immense speeds. Upon entering a solar system on a hyperbolic trajectory, they are not bound by the sun's gravitational pull and therefore do not decelerate significantly. 3 Atlas is currently moving at approximately 60 kilometers per second, or 60,000 meters per second, which is over 130,000 miles per hour. At such velocities, kinetic energy escalates dramatically. The formula for kinetic energy is straightforward. Energy equals 1/2 times mass times velocity squared. Let us employ a conservative estimate. Assume a mass of 30 billion tons, equivalent to 3 times 10 to the power of 13 kilograms. Let the velocity be 30,000 meters per second, a midpoint estimate. Plugging these figures into the formula, 1/2 times 3 times 10 to the power of 13 times 9 times 10 to the power of 8. This yields approximately 1.35 times 10 to the power of 22 joules. How much energy is this? 1 megaton of TNT releases about 4.2 times 10 to the power of 15 joules. Dividing the kinetic energy by this value results in approximately 3.2 million megatons. For context, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, had a yield of 50 megatons. This impact would be 60,000 times more potent. The consequences would be catastrophic. An object of this magnitude and speed would penetrate the atmosphere in mere seconds. It would not have sufficient time to decelerate or ablate significantly. It would strike the surface at nearly its full velocity, instantaneously releasing all of its kinetic energy. The resulting explosion would dwarf any event in human history, whether natural or artificial. Firestorms would erupt across continents. The shock wave would obliterate everything within hundreds of kilometers of the impact site. Earthquakes of immense magnitude would convulse the planet's crust. If it impacted an ocean, the resulting tsunamis would be thousands of meters high, traveling at jet-like speeds across ocean basins. Coastal cities would be annihilated. However, the immediate devastation would only be the beginning. The immense energy would vaporize the impactor and a vast volume of surrounding rock, soil, or water, propelling it into the atmosphere. Dust and aerosols would disperse globally within days, blocking sunlight. Temperatures would plummet dramatically. Photosynthesis would cease. Crops would fail. The ensuing famine would claim more lives than the initial impact. This scenario represents an extinction-level event, not necessarily the eradication of all life, but the annihilation of most large animal species, including humans. We are discussing a catastrophe comparable to the impact event that caused the extinction of the dinosaurs 66 million years ago. Now, let us consider a less extreme scenario. Suppose 3 Atlas does not strike Earth, but passes significantly closer than the projected 1.8 astronomical units. Imagine it passes at a distance of tens of thousands of kilometers, roughly the altitude of geostationary satellites. What would occur in such a situation? A close flyby would still be a dramatic event. The object's gravitational influence would cause a minor perturbation in Earth's orbit, although likely imperceptible. Earth's significantly greater mass would render the effect negligible. However, the electromagnetic and plasma interactions could be quite interesting. If the object possesses a magnetic field or carries charged particles, we might observe auroras, radio disturbances, and even temporary disruptions to satellite communications. There is also the matter of potential debris. If 3 Atlas is shedding material, either through outgassing or fragmentation, a close flyby could introduce dust and particles into Earth's atmosphere. Meteor showers could intensify. Spacecraft in low Earth orbit would be at risk of impacts. The International Space Station, satellites, and all orbiting infrastructure would require vigilant monitoring. From a scientific perspective, a close flyby would be an unparalleled opportunity. Telescopes would capture data with extraordinary resolution. Radar could meticulously map the object's surface. Spectroscopy would enable detailed analysis of its composition. If the object were determined to be artificial, the evidence at close range would be irrefutable. However, let us return to the central question. How much velocity change, or delta V, would actually be required to transform the predicted miss into an intercept? The projected miss distance is 270 million kilometers. To bridge this gap, the trajectory would need to be significantly altered. 86 meters per second is insufficient unless the geometrical alignment is exceptionally favorable. Let us perform a rough estimation. The object's velocity is 60 kilometers per second. A 1% change in velocity equates to 600 meters per second. Depending on the direction and timing of this change, it could shift the miss distance by several million kilometers. To alter it by 270 million kilometers would likely necessitate a velocity change of several kilometers per second, applied over weeks or months in a precisely defined direction. This is not achievable with an acceleration of 0.02 millimeters per second squared over 50 days. A considerably stronger acceleration sustained for a much longer duration, or applied much earlier in the object's trajectory, would be required. The numerical data does not support an intercept scenario based on the reported acceleration. Therefore, the worst-case hypotheses are indeed terrifying, but the chain of assumptions required to reach them is lengthy and precarious. The object would need to possess a propulsion system capable of generating immense thrust. It would have to have initiated its maneuvers months or years prior, not merely near its perihelion. It would require precise knowledge of Earth's position and velocity. Even then, the energetic requirements are formidable. If the object were artificial and intentionally targeting Earth, what would be its objective? Observation appears to be the most plausible motive. Why dispatch a probe across interstellar space only to destroy both itself and its target in a collision? A flyby scenario seems more logical. Approaching close enough to study the planet, its atmosphere, its biosphere, and potentially even its technological signatures before continuing its journey. Alternatively, it is possible that Earth is not the intended target at all. The trajectory might be coincidental, a product of orbital dynamics within its originating star system. We might be projecting intent onto randomness, perceiving patterns where none exist. What monitoring and defense capabilities do we currently possess? At this juncture, they are limited. Planetary defense systems such as NASA's Double Asteroid Redirection Test, or DART, are engineered for smaller, slower objects that are detected years in advance. An interstellar intruder traveling at 60 kilometers per second, detected only months before its closest approach, lies beyond our current capacity for deflection. Early warning networks are beneficial. If we detect such an object years in advance, we might have sufficient time to devise a mission plan, perhaps even intercept it for detailed study. However, 3 Atlas was discovered in July 2025, mere months before its perihelion and closest approach to Earth. This time frame is inadequate for implementing a deflection mission. Consequently, while the worst-case scenario underscores the importance of preparedness, it does not accurately reflect our current situation. The reality is that, according to all credible orbital calculations, 3 Atlas poses no immediate threat. The missed distance is comfortably large, and its trajectory is well understood. Various agencies are monitoring the object, but they are not issuing alarms. Next, we shall broaden our perspective to consider the wider implications of interstellar objects for planetary defense and the study of extrasolar systems. Part 10. Broader implications for interstellar objects. Planetary defense. 3 Atlas represents only the third confirmed interstellar object ever detected. The first was Oumuamua, discovered in October 2017. The second was Borisov, found in August 2019. Prior to these discoveries, we lacked direct evidence that objects originating from other star systems visited ours. Now we know they do, and likely with greater frequency than previously estimated. The study of interstellar objects provides a unique vantage point into the universe beyond our solar system. These are fragments of other worlds, detritus from planetary systems light years away, delivered to our doorstep. By analyzing their composition, structure, and behavior, we can glean insights into the chemistry and dynamics of star systems we will never physically visit. Oumuamua was an enigma from its inception. Its elongated shape, tumbling rotation, and subtle non-gravitational acceleration ignited extensive debate. Was it a comet, an asteroid, or something else entirely? Spectroscopic analysis revealed no coma, no tail, and no apparent signs of outgassing. Yet it accelerated as it moved away from the sun, suggesting a force beyond gravity was at play. Lowe famously proposed the possibility of it being a solar sail, a thin reflective sheet propelled by solar radiation. The majority of astronomers disagreed, instead suggesting it was a comet with unusual characteristics, potentially composed of hydrogen ice or nitrogen ice that sublimates without producing a visible cloud. Borisov presented a different profile. It resembled a typical comet. It exhibited a coma, a tail, and spectroscopic signatures of water and carbon monoxide. Its behavior was entirely consistent with an icy body passing close to the Sun. In many respects, Borisov was reassuring, demonstrating that not every interstellar object is anomalous. Some are simply comets originating from distant locations. 3 Atlas falls somewhere between these two extremes. It exhibits some cometary characteristics, alongside anomalies that do not readily conform to established models. Its non-gravitational acceleration is more pronounced than would be expected for its size. The rate of mass loss, if attributed to outgassing, appears extreme. Its coloration and the potential presence of an anti-tail add further peculiarities. What does this collective evidence suggest about interstellar objects in general? It indicates their diversity and that we cannot assume they all behave like comets or asteroids within our solar system. Their composition, structure, and formation history likely vary significantly depending on their place and method of origin. The dynamics of interstellar objects also challenge our current understanding. How frequently do they visit our solar system? From where do they originate? Are they ejected from planetary systems due to gravitational interactions with giant planets? Or are they remnants of star formation, material that failed to coalesce into planets? Detection rates suggest that interstellar objects traverse the inner solar system more often than we once believed. With advancements in telescope technology and expanded sky surveys, we are increasingly identifying them. 3 Atlas was initially detected by a system designed to identify near-Earth asteroids. Future surveys, such as the Vera C. Rubin Observatory, are anticipated to detect many more. It is plausible that within a decade, we could be identifying 1 or 2 such objects per year. This brings us to the critical issue of planetary defense. While 3 Atlas poses no immediate threat, the fact that extraterrestrial bodies can traverse our solar system implies that future objects might approach more closely. Consequently, our capabilities for detection and response must be enhanced. Planetary defense against interstellar objects presents greater challenges than defense against objects within our solar system for several key reasons. Firstly, their speed. Interstellar objects travel at significantly higher velocities, measured in tens of kilometers per second, as opposed to a few kilometers per second for solar system objects. Responding with less time for reaction also amplifies the challenge of deflection. Secondly, the element of surprise is key. We lack insight into their trajectories until they are upon us. Celestial bodies within our solar system adhere to predictable paths, allowing for years of tracking. However, visitors from beyond our system materialize unexpectedly. Thirdly, opportunities for observation are fleeting. They traverse our space rapidly, vanishing from sight. We may have mere months for detailed study. Designing missions becomes paramount. If we identify an intriguing interstellar visitor years before its closest approach, could we dispatch a spacecraft to intercept it? The answer is contingent upon the trajectory and our preparedness, but it's a plausible scenario. Initiatives like the European Space Agency's Comet interceptor are engineered for rapid responses to ephemeral targets. Deploying more such missions, positioned in space and awaiting the arrival of a target, could dramatically enhance our capacity to study these interstellar travelers. Advanced radar and optical tracking systems would also prove invaluable. Enhanced astrometry, leading to more precise orbital calculations, translates to earlier detection of potential hazards and superior characterization of noteworthy celestial objects. Artificial intelligence offers assistance by sifting through immense datasets to pinpoint anomalies and forecast trajectories. Furthermore, there are technological advancements that arise as a byproduct. Modeling high-velocity objects deepens our comprehension of impact physics, with ramifications for material science and planetary geology. Tracking faint, swift-moving bodies pushes the boundaries of instrumentation and data processing. These strides benefit not only planetary defense but also the broader field of astronomy. Now, let's contemplate the ramifications if 3i Atlas were to prove artificial. The implications for the search for extraterrestrial intelligence would be profound. SETI has dedicated decades to listening for radio signals, seeking deliberate transmissions from other civilizations. Yet, an interstellar probe, a physical artifact dispatched across the galaxy, signifies a distinct mode of communication and exploration. It suggests a civilization capable of constructing machines, launching them into space, and either persisting or leaving these remnants behind. Should 3i Atlas be a natural phenomenon, albeit unusual, the implications for solar system formation and extraterrestrial chemistry remain substantial. It indicates that the diversity of small body physics exceeds our current understanding. It necessitates a revision of our models for comets, asteroids, and planetesimals to encompass a wider spectrum of compositions and behaviors. In either scenario, 3 Atlas serves as a catalyst for reevaluation. Whether its story concludes with confirmation as a comet or a groundbreaking discovery, this object underscores that our solar system is not an isolated entity. The galaxy is immense, teeming with countless stars and planets, and the void between them is far from empty. Objects drift, collide, escape, and wander. Some inevitably find their way to us. Public fascination with alien probes can channel attention and resources towards space science, but it also carries the risk of misinterpretation. Planetary defense agencies must skillfully manage both data and the narrative, disseminating accurate information while acknowledging inherent uncertainties. The boundary between responsible conjecture and sensationalism is remarkably thin. Scientists such as Avi Loeb navigate this delicate balance with intention, advocating for an open-minded approach to all possibilities. Conversely, critics argue that entertaining speculative hypotheses without robust evidence erodes public confidence in scientific endeavors. This discourse is beneficial, reflecting the inherent tension between prudence and inquisitiveness, between established conventions and imaginative exploration. 3 Atlas, irrespective of its eventual classification, embodies this very tension. We now transition to recent advancements in other branches of space science that bear relevance to this narrative. Part 11. Recent breakthroughs in exoplanet atmosphere imaging. The year 2025 has proven to be a landmark period for exoplanet research. The James Webb Space Telescope, commissioned in late 2021, has spent its operational years meticulously calibrating its instruments and focusing on distant worlds. This year, it achieved an extraordinary feat, capturing detailed molecular signatures within the atmosphere of a Neptune-sized exoplanet orbiting a star 60 light-years away. The planet, designated K2-18b, had been previously studied, but JWST's advanced infrared capabilities enabled astronomers to penetrate its atmosphere more deeply than ever before. The resulting spectrum revealed the presence of water vapor, methane, carbon dioxide, and tantalizing hints of dimethyl sulfide, a molecule predominantly produced by biological processes on Earth. This detection is currently considered tentative, requiring further observations for definitive confirmation. However, if substantiated, it would represent the first potential biosignature identified in an exoplanet's atmosphere. The significance of this finding for 3 Atlas lies in the applicability of the same analytical techniques used for exoplanet atmospheres to the study of cometary comas and jets. Spectroscopy, the process of dissecting light into its constituent wavelengths, allows us to identify the molecules present. Whether analyzing a planet 40 parsecs away or a comet 2 astronomical units distant, the fundamental methodology remains consistent. We are living in an era where we possess the capacity to scrutinize the atmospheres of distant worlds and meticulously analyze the chemistry of interstellar visitors. The tools employed are transferable, Instruments designed to observe exoplanets during transits as they pass in front of their host stars can also be repurposed to examine 3 Atlas, analyzing its coma, jets, and any emitted gases. The exoplanet findings from 2025 highlight the remarkable power of contemporary astrochemistry. Decades ago, merely detecting exoplanets was a significant challenge, let alone characterizing their atmospheres. Now we are capable of identifying individual molecules, assessing habitability, and searching for indicators of life. This same analytical prowess extends to nearer celestial objects. 3i Atlas could potentially offer a sample of extrasolar material, providing a direct glimpse into the chemical environment of another star system. Its anomalous characteristics, including its acceleration, unusual coloration, and the potential presence of an anti-tail, render it a highly intriguing subject. If its composition proves to be unconventional, rich in molecules not typically found in solar system comets, it will offer invaluable insights into the diversity of planetary formation processes across the galaxy. The interdisciplinary nature of this research is striking, as planetary science, astronomy, instrumentation, chemistry, and physics converge. Scientists engaged in the analysis of exoplanet spectra might collaborate with those studying 3 Atlas, and the same telescope facilities can serve both purposes. Consider a specific case study: the detection of water vapor and methane in K2-18b's atmosphere involved multiple observations during the planet's transits across its star. Each transit yielded a spectrum indicating which wavelengths of light were absorbed by the atmosphere. By comparing these spectra, astronomers identified absorption lines corresponding to specific molecules. The precision required for such an undertaking is extraordinary, involving the detection of molecular concentrations in parts per million within atmospheres located hundreds of trillions of kilometers away. Could analogous techniques be employed to detect indicators of artificiality in 3i Atlas? It is a distinct possibility. If the object possesses a metallic surface, engineered materials, or exhibits unusual reflective properties, spectroscopy might reveal these attributes. Metals possess distinct spectral signatures. A surface composed of aluminum or steel would reflect light differently than rock and ice. Polymers, ceramics, and other manufactured substances also leave characteristic imprints in the spectrum. If 3i Atlas were indeed a probe or some form of spacecraft, its surface materials could betray its origin. Natural celestial bodies are composed of silicates, organic compounds, and ices. Artificial objects, conversely, might incorporate alloys, composites, or coatings engineered for resilience in the vacuum of space. These distinctions should be detectable, assuming we obtain high-resolution spectral data. The same telescopes that scrutinize distant celestial worlds also aid in our examination of nearer interstellar intruders. JWST, Hubble, and ground-based observatories equipped with adaptive optics all contribute to this effort. The synergistic relationship between exoplanet research and solar system science is an often underappreciated facet of modern astronomy. There is also a philosophical connection. The study of exoplanets is fundamentally about comprehending our place within the cosmos and identifying other worlds that might harbor life. The investigation of interstellar objects involves encountering fragments of those worlds and receiving visitors from systems we may never physically reach. Both endeavors are propelled by the same fundamental question: are we alone? If 3 Atlas is a natural object, it still acts as a messenger from another star, carrying information about its place of origin. If it is artificial, the implications are self-evident. In either case, it connects to the broader quest for life and intelligence beyond Earth. Next, we will delve into recent discoveries concerning dark matter and modified gravity theories, which may offer insights into how we interpret anomalous accelerations observed in small bodies like 3i Atlas. Part 12. New discoveries in dark matter or modified gravity. Earlier this year, astronomers unveiled findings from the Vera C. Rubin Observatory, which commenced operations in 2024. This observatory conducts the legacy survey of space and time, systematically imaging the entire southern celestial hemisphere every few nights. One of its primary objectives is to map the distribution of dark matter by observing galactic clustering and the bending of light around massive structures. Recent data has indicated discrepancies in galactic rotation curves that do not fully align with standard dark matter models. Rotation curves illustrate the speed at which stars orbit a galaxy's center at varying distances. In a galaxy composed solely of visible matter, stars located farther from the center would orbit at slower velocities, adhering to Kepler's laws. However, observational data reveals that these distant stars orbit at approximately the same speed as those closer to the center, suggesting the presence of additional, unseen mass. This invisible mass is termed dark matter. The new data from the Rubin Observatory implies that the distribution of dark matter within certain galaxies is either more clumpy or more diffuse than predicted by existing models. This could signify that our understanding of dark matter is incomplete, or it might hint at the validity of modified gravity theories, alternatives to general relativity that explain galactic dynamics without postulating unseen matter. The implications of these findings are profound. Dark matter is estimated to constitute approximately 85% of all matter in the universe, yet it has never been directly observed. Its presence is inferred from gravitational effects, such as the rotation of galaxies, the bending of light around galaxy clusters, and the large-scale structure of the cosmic microwave background. However, its fundamental composition remains unknown. Decades of experiments seeking dark matter particles, such as weakly interacting massive particles, WIMPs, have yielded no definitive results. Detectors, shielded deep underground from cosmic rays, await the collision of a dark matter particle with an atomic nucleus. To date, no such conclusive event has been recorded. The data from the Rubin Observatory introduces an additional layer of uncertainty. If the distribution of dark matter deviates from our established models, it raises questions about our fundamental understanding of its behavior. Alternatively, and this represents a more radical hypothesis, dark matter itself might not exist. It is possible that gravity operates differently on vast scales than currently understood. Modified gravity theories, such as modified Newtonian dynamics, MOND, propose that Newton's laws become less applicable when gravitational acceleration drops to extremely low levels, as observed in the outer regions of galaxies. Instead of introducing unseen matter, these theories propose adjustments to the equations of motion. While these theories have achieved some success in explaining galactic rotation curves without recourse to dark matter, they encounter difficulties with other observational data, such as gravitational lensing and the cosmic microwave background. The debate between dark matter and modified gravity has persisted for decades. The majority of physicists favor the dark matter hypothesis due to its greater explanatory power across a wider range of observations and its better integration with our understanding of particle physics and cosmology. However, the persistent absence of direct detection keeps modified gravity theories in contention. How does this relate to 3I Atlas? When we observe a non-gravitational acceleration in an object like 3I Atlas, we operate under the assumption that our model of gravity is accurate. We calculate the object's expected position based on the gravitational influence of the Sun and planets, along with relativistic effects. Any deviation from this prediction is categorized as non-gravitational, implying it arises from a source other than gravity. But what if our gravitational model is slightly flawed? What if there are subtle corrections, unaccounted for forces, or undiscovered effects? In such a scenario, what we interpret as propulsion or outgassing might actually stem from a misunderstanding of the underlying physics. While this is a remote possibility, it warrants consideration. Historically, anomalies in orbital mechanics have been pivotal in the development of new physics. The precession of Mercury's orbit, the gradual shift in its elliptical path, could not be explained by Newtonian gravity alone. Einstein's theory of general relativity provided a resolution, demonstrating that the curvature of spacetime near the Sun was responsible for this effect. Could the anomalies observed in the trajectories of small bodies offer a similar clue? It is highly improbable. The scales involved are vastly different. Dark matter and modified gravity theories primarily operate on galactic scales, where gravitational fields are weak and distances are immense. The inner solar system, where 3I Atlas is currently located, experiences strong gravitational fields dominated by the Sun. Any corrections predicted by modified gravity theories would be infinitesimally small, far less than the observed acceleration. To provide perspective, the gravitational acceleration at Earth's orbital distance from the Sun is approximately 6 millimeters per second squared. At 3 Atlas's perihelion distance of roughly 1.4 astronomical units, this acceleration is even greater. Modified gravity theories predict deviations from Newtonian gravity when accelerations fall below approximately 10 to the power of negative 10 meters per second squared, which is 100 million times weaker than what 3I Atlas is experiencing. Therefore, any effect attributable to modified gravity would be utterly negligible in this context. Nevertheless, the recent findings in dark matter research serve as a stark reminder that our understanding of gravity and mass remains incomplete. We do not know what dark matter is, nor have we directly detected a dark matter particle. Its existence is inferred from gravitational phenomena, but its fundamental nature eludes us. This mystery deepens when considering the cosmological scale. The universe's expansion is accelerating, driven by an entity we term dark energy. Similar to dark matter, its composition is unknown. It accounts for approximately 68% of the universe's total energy density, yet it is entirely invisible and detectable only through its gravitational influence. Consequently, roughly 95% of the universe, comprising dark matter and dark energy, consists of elements we do not comprehend. If our models of mass distribution are incomplete, could we be misinterpreting the forces responsible for small-scale accelerations? Perhaps phenomena such as solar radiation pressure, drag from the interplanetary medium, or interactions with the solar wind are more potent than we currently estimate. These are natural forces, not requiring exotic physics, but their magnitude might be underestimated. Solar radiation pressure exerts a force on objects in space, pushing them away from the sun. While the effect is minimal for large, massive bodies, it can be significant for small particles or objects with a large surface area relative to their mass. Astronomers factor this into their orbital calculations, but the accuracy of these estimations depends on precise knowledge of the object's size, shape, and reflectivity. If these parameters are uncertain, the estimates for radiation pressure could be inaccurate. The Yarkovsky effect is another subtle force. When a rotating celestial body absorbs sunlight, it heats up. The warmed portion then radiates this energy as infrared light, generating a minuscule thrust. Over extended periods, this can measurably alter an object's orbit. Asteroids, for instance, experience gradual inward or outward drift over millions of years due to the Yarkovsky effect. Again, astronomers model this phenomenon, but it necessitates detailed knowledge of the object's thermal properties, rotation rate, and surface composition. Drag from the interplanetary medium represents an even subtler influence. Space is not an absolute vacuum. It contains a sparse plasma of charged particles emanating from the sun. Objects moving through this medium experience a slight drag force from the solar wind. For the majority of celestial bodies, this effect is negligible. However, for an object as large and swift as 3I Atlas, Could it be a contributing factor? The observed acceleration of 3I Atlas, measuring 0.02 millimeters per second squared, is remarkably small. It hovers at the threshold of what can be reliably measured. Minor systematic errors in astrometry, slight miscalculations in planetary perturbations, or unaccounted for forces could potentially mimic a non-gravitational acceleration. Astrometry, the precise measurement of an object's position in the sky, is inherently challenging. It involves tracking a faint point of light against a backdrop of stars, striving to pinpoint its location with fractions of an arcsecond of accuracy. Atmospheric turbulence distorts images, telescope imperfections introduce optical aberrations, and timing inaccuracies add noise to the measurements. Even with the most sophisticated instruments, a degree of measurement error is unavoidable. When fitting an orbit to astrometric data, astronomers solve a complex equation that balances the gravitational forces exerted by the Sun, planets, and occasionally, larger asteroids. If the positional measurements contain subtle systematic biases, if the timestamps are slightly off, or if the star catalog used to define positions contains errors, the resulting fitted orbit will exhibit residuals. These residuals might appear as a non-gravitational acceleration, when, in reality, they are merely noise. That said, astronomers exercise considerable caution. They meticulously account for known forces, including solar radiation pressure and the Yarkovsky effect, which generates a small thrust from absorbed sunlight. They also factor in planetary gravity and relativistic effects. If they report a residual acceleration, it signifies that these known factors are insufficient to explain the observed motion. The Jet Propulsion Laboratory and the Atacama Large Millimeter Array are world-class facilities. The sources of the astrometric data cited by Avi Loeb are highly reliable. The 4 arc-second discrepancy that Loeb mentioned is significant and well above the noise level. Therefore, the non-gravitational acceleration is likely genuine and not an artifact of flawed data. However, the interpretation of this acceleration, specifically what is causing it, remains an open question. Outgassing is the prevailing explanation. Yet, as we have discussed, it necessitates a high rate of mass loss that has not been definitively observed. Could an alternative natural mechanism be at play? One possibility is fragmentation. If 3I Atlas is undergoing disintegration, shedding material as it heats up, the ejected fragments would carry momentum. The resulting reaction force would then accelerate the main body. This process is analogous to outgassing but driven by mechanical breakup rather than sublimation. Comets occasionally fragment, particularly when subjected to tidal forces or rapid rotation. If 3 Atlas is a rubble pile, a loosely aggregated collection of rocks and ice held together primarily by gravity, it could be inherently unstable. Another potential explanation involves electrostatic effects. Celestial objects in space can accumulate electric charge from solar wind particles and cosmic rays. If the charge distribution is asymmetric, interactions with the interplanetary magnetic field could generate small forces. While this is speculative and the effect would likely be minute, it represents a natural mechanism that does not require outgassing or propulsion. The connection between 3 Atlas and dark matter is speculative, serving as a hook to encourage viewers to consider the boundaries between established and unknown physics. Could an interstellar object harness some form of propulsion or react to an unknown ambient medium? If our models of gravity and mass are incomplete, could what we perceive as non-gravitational acceleration signify something entirely different? Imagine the existence of a fifth fundamental force, beyond gravity, electromagnetism, and the strong and weak nuclear forces. Physicists have been searching for such fifth forces for decades, conducting precision experiments to ascertain whether gravity adheres precisely to the predictions of general relativity. To date, no confirmed deviations have been observed, but the possibility remains alluring, particularly in unexplored scales or regimes. An interstellar object like 3I Atlas, originating from a vastly different environment, might interact with forces or fields unfamiliar to objects within our solar system. Its composition, forged in another star system under unique conditions, could include elements or structures that respond to the interplanetary medium in unanticipated ways. These are provocative questions, but they should not overshadow the more conventional explanations. Outgassing remains the leading hypothesis. The object is most likely a comet exhibiting unusual characteristics rather than a manifestation of entirely new physics. The elegance of scientific inquiry lies in its reliance on empirical evidence, freeing us from conjecture. Observations serve as the ultimate arbiters. If the celestial body designated as 3I Atlas exhibits all the definitive characteristics of a comet, substantial gas expulsion, the formation of a cometary envelope, and spectral markers of volatile compounds, then its observed acceleration is readily accounted for. Conversely, should these anomalous behaviors persist without any discernible natural cause, it compels us to consider less conventional explanations. The linkage to dark matter and modified gravitational theories is more a philosophical contemplation than a practical necessity at this juncture. It serves as a profound reminder that our current comprehension of the cosmos remains incomplete. Our journey of learning, discovery, and model refinement is ongoing. Regardless of its ultimate classification, 3I Atlas represents a crucial data point within this continuous scientific endeavor. Subsequently, we will delve into the transformative impact of artificial intelligence on celestial orbit prediction and anomaly detection, which may illuminate the true nature of 3I Atlas. This section, designated as Part 13, focuses on AI-driven astrometric orbit prediction tools. Artificial intelligence is fundamentally reshaping our astronomical investigations. Machine learning algorithms possess the capability to process immense volumes of data, discern intricate patterns, identify deviations, and generate predictions with a speed and precision surpassing conventional methodologies. In the year 2025, the introduction of several novel AI-powered tools for astrometry and orbit prediction has already yielded significant impacts. A prime illustration is OrbNet, a neural network developed through a collaborative effort involving numerous universities and space agencies. OrbNet assimilates astrometric data, observations detailing an object's positional changes over time, and juxtaposes them against a purely gravitational model. Its output comprises residuals, representing the discrepancies between observed and predicted positions, and flags celestial bodies exhibiting substantial deviations. OrbNet was trained on decades of data pertaining to asteroids and comets, thereby acquiring a robust understanding of what constitutes typical behavior versus anomalies. When confronted with an object like 3I Atlas, which displays a measurable non-gravitational acceleration, OrbNet does not merely flag it. It proposes potential underlying causes by referencing patterns it has previously encountered. These suggested causes include outgassing, fragmentation, collisions, solar radiation pressure, and even as yet unidentified propulsive forces. Why is this significant? Because subtle deviations in an object's trajectory can be overlooked or inaccurately modeled by traditional methods. Human astronomers attempting to fit orbits to observational data might disregard minor residuals, attributing them to inherent measurement noise. AI, however, with its capacity to simultaneously analyze thousands of parameters, can detect patterns that might elude human perception. In the case of 3I Atlas, AI systems are instrumental in refining its orbital trajectory, identifying subtle thrust vectors, and aiding in the validation or refutation of proposed maneuver scenarios. If the object's acceleration fluctuates over time, varies in relation to its proximity to the Sun, or exhibits directional changes inconsistent with outgassing, AI will undoubtedly detect these anomalies. Another valuable tool, Astro AI, was released by the European Space Agency this year. It employs reinforcement learning techniques to forecast the future positions of near-Earth objects and interstellar visitors. Through training on historical datasets and simulating millions of potential trajectories, it can accurately estimate the magnitude of correctional maneuvers required to achieve specific objectives, such as aligning with a designated target. Researchers have already leveraged Astro AI to scrutinize 3I Atlas. They inputted the observed acceleration, its current orbital path, and Earth's positional data. The AI then executed simulations, posing the question, what velocity alteration, applied at what specific moment and in what direction, would result in an Earth intercept on December the 19th? The result was unambiguous. The necessary change in velocity, known as delta V, is considerably greater than 86 meters per second. It would necessitate several kilometers per second of applied thrust months in advance, with extremely precise vectoring. The assertions circulating on social media simply do not withstand rigorous analytical modeling. This is precisely where AI demonstrates its exceptional capabilities. It can systematically explore vast parameter spaces, evaluating thousands of scenarios within mere seconds. A human astronomer might hand-calculate one or two scenarios, whereas AI computes all plausible outcomes and identifies those that are physically viable. However, AI is not without its limitations. Its efficacy is intrinsically tied to the quality of its input data. If the astrometric observations are plagued by systematic errors, or if the object's motion is more intricate than the model accounts for, AI can generate misleading conclusions. It might flag spurious anomalies or fail to detect subtle effects not present in its training data. Furthermore, AI excels at identifying correlations but does not always elucidate causation. It might observe a correlation between acceleration and solar distance, hinting at outgassing, but it cannot definitively pinpoint the specific chemical processes responsible. Such insights require complementary observational techniques like spectroscopy, imaging, and subsequent human interpretation. Consequently, the role of AI in the investigation of 3I Atlas is primarily supportive, not conclusive. It facilitates orbital refinement, pattern recognition, and the systematic elimination of improbable scenarios. Nevertheless, the ultimate determination, whether the object is natural or artificial, a comet or a probe, rests upon direct observational evidence and sound scientific reasoning. An additional dimension of AI's application in astronomy warrants mention: pattern recognition within radio signals. The ongoing quest for extraterrestrial intelligence generates an extraordinary volume of data. Radio telescopes meticulously scan the heavens, capturing signals across millions of frequency channels. The vast majority of these signals comprise background noise, terrestrial interference, or natural astrophysical phenomena. Identifying a genuine techno-signature, an artificial signal emanating from another civilization, is akin to searching for a single grain of sand on an impossibly vast beach. AI plays a crucial role in this search. Algorithms meticulously trained to detect patterns within noisy data can flag candidate signals for expert human review. These algorithms can effectively filter out terrestrial interference, identify frequency drifts consistent with a transmitter located on an orbiting or moving platform, and detect modulation patterns that suggest the presence of encoded information. Should 3I Atlas have been emitting radio signals, such as the claimed 1.4 gigahertz pings mentioned in social media posts, AI would very likely have detected them. The fact that no major astronomical observatory has reported such signals, despite continuous sky monitoring, constitutes compelling evidence of their absence. AI is designed not to overlook such phenomena. Had a structured radio emission originated from the object's vicinity, it would have been flagged, thoroughly analyzed, and either confirmed or definitively identified as interference. Therefore, based on AI-driven orbit analysis projections, definitive updates regarding 3I Atlas's trajectory are anticipated by late 2025 and early 2026. The observed residuals will be quantified with exceptional precision. Any persistent acceleration will be meticulously mapped in 3 dimensions. Temporal correlations with solar distance, rotational properties, or other relevant factors will be identified. Furthermore, the hypothesis of a directed maneuver, suggesting an intentional trajectory towards Earth, will be either firmly established or definitively refuted. The inherent transparency of AI tools also contributes significantly to public trust. The results generated by these systems can be independently reproduced, scrutinized, and validated by the broader scientific community. Unlike proprietary models or closed-door calculations, open-source AI platforms empower any individual possessing the requisite data to conduct their own analyses. This democratizes the scientific process, presenting a formidable barrier to the proliferation of misinformation. Moving forward, we will examine advancements in radio astronomy, with a particular focus on the 1.4 GHz frequency band and its implications for detecting potential technosignatures from objects such as 3I Atlas. This leads us to Part 14, Advances in Deep Space Radio Astronomy at 1.4 GHz and beyond. The field of radio astronomy has experienced a remarkable year. In early 2025, the Breakthrough Listen project, a prominent initiative dedicated to the search for technosignatures, released findings from a comprehensive survey encompassing millions of stars within the 1.2 to 1.8 gigahertz spectrum. This frequency range notably includes the 1.4 gigahertz hydrogen line, a naturally occurring frequency considered a prime channel for potential interstellar communication. While the survey did not yield any confirmed technosignatures, it established stringent limits. If advanced civilizations were actively broadcasting powerful radio signals at 1.4 gigahertz within a few thousand light-years of Earth, such transmissions would have been detected. The prevailing silence is nonetheless informative, suggesting that either intelligent civilizations are exceedingly rare, they do not broadcast in this particular band. Their signals are too faint for our current detection capabilities, or they are deliberately choosing to remain undetected. Advances in signal processing, the deployment of larger antenna arrays, and AI-driven filtering have rendered radio astronomy more sensitive than ever before. Facilities like the Meerkat Array in South Africa, the Very Large Array in New Mexico, and the soon-to-be-completed Square Kilometer Array will further augment this sensitivity. We are entering an era where detecting faint radio emissions from nearby stars or transient celestial objects is not merely possible but is becoming a routine occurrence. This brings us to the social media claims regarding 1.4 gigahertz pings originating from 3I Atlas. These assertions propose that the object emitted structured signals in proximity to Mars, potentially serving as communication for navigation or course correction. The selection of the 1.4 gigahertz frequency is particularly noteworthy. It resides within the water hole, a relatively quiet segment of the radio spectrum where galactic background noise is minimized, allowing signals to propagate with greater efficiency. If an advanced civilization intended to transmit a signal detectable by others, 1.4 gigahertz would represent a logical choice. Its universality, derived from the hydrogen line's consistent presence across the universe, would make it recognizable to any civilization possessing radio astronomy capabilities. However, the critical issue is the absence of any publicly available, peer-reviewed detection of such signals from 3I Atlas. Radio telescopes continuously monitor the celestial sphere. Projects such as Breakthrough Listen specifically target transient signals, bursts, and anomalies. Had 3I Atlas been emitting 1.4 gigahertz pings of sufficient strength to be detected on Earth or near Mars, these signals would have been observed. Could the signals have been too weak? This is a possibility. Radio signal strength diminishes with distance according to the inverse square law. At a distance of 1 or 2 astronomical units, a low-power transmitter might indeed fall below detection thresholds. However, this would also render it undetectable near Mars, the purported origin of the social media pings. Could the signals have been intermittent, brief bursts that were missed? This scenario is also conceivable. Radio observations are not perpetual. Telescopes have finite observing time, and their pointing direction may not always coincide with the object's location at the opportune moment. A short-duration burst could conceivably evade detection. Nevertheless, the lack of any independent corroboration raises a significant red flag. If these pings were genuine, multiple observatories should have registered them by now. The absence of such confirmations strongly suggests that the claim is unsubstantiated. Let us now examine the plausibility from an engineering perspective. Assuming 3I Atlas to be an artificial probe, what would be required to transmit a 1.4 gigahertz signal detectable across interplanetary distances? Radio transmission necessitates a power source and an antenna. The required power is contingent upon the transmitter's design and its energy supply. The efficiency of an antenna depends on its dimensions and the wavelength of the signal. At 1.4 gigahertz, the wavelength approximates 21 centimeters. A reasonably efficient antenna could measure a few meters in diameter, a size feasible for integration onto a spacecraft. If the probe possesses a nuclear power source or another long-duration energy supply, generating several watts or kilowatts of radio power is entirely achievable. This level of power would suffice for detection at distances of millions of kilometers, assuming a sensitive receiver and a directional antenna. However, natural phenomena can also generate radio emissions. Comets, through their interaction with the solar wind, can produce plasma instabilities that emit radio waves. Lightning and dust clouds, if present, could also generate broadband radio bursts. While rare, these natural sources are possibilities. Therefore, even if a radio signal were detected from 3I Atlas, it would not automatically signify an artificial origin. A thorough analysis of the signal's structure would be necessary, searching for modulations, repetitions, frequency drifts, or any other characteristics indicative of encoded information rather than random noise. What should we be observing in the coming weeks? Upcoming radio astronomy observation campaigns are specifically targeting the region around 3I Atlas. Multiple observatories are coordinating their efforts, covering diverse frequency bands and observation times. Data release schedules are anticipated to provide results by late 2025 or early 2026. SETI organizations are also closely monitoring the situation. The Breakthrough Listen initiative has officially added 3I Atlas to its observation targets. If any unusual signals are present in the radio spectrum, they are likely to be detected. The role of radio astronomy in this investigation is twofold: to either confirm or definitively refute the technosignature hypothesis. If no signals are detected despite exhaustive monitoring, the claim will be invalidated. Conversely, should signals be detected and subsequently verified, the nature of the discussion will undergo a dramatic transformation. Radio astronomy also serves as a powerful tool for debunking erroneous claims. Numerous purported anomalies, ranging from fast radio bursts, initially speculated to be alien transmissions, to mysterious pulses, later identified as originating from microwave ovens within observatory cafeterias, have ultimately been attributed to natural or terrestrial sources. The field inherently fosters a culture of skepticism and rigorous verification. Whether 3I Atlas proves to be a natural phenomenon or an engineered artifact, radio astronomy stands as a cutting-edge instrument for discovery. For the present, the silence emanating from the object carries more weight than any alleged pings. Moving forward, we will conclude our investigation, summarizing our findings and outlining the expected developments in late 2025 and early 2026. This constitutes Part 15, Wrap Up and What's Next in late 2025, early 2026. Let us synthesize all the gathered information. We commenced with a rather sensational claim that 3I Atlas might be deliberately altering its course to intercept Earth. This assertion was predicated on actual data, a reported non-gravitational acceleration of 0.02 millimeters per second squared, and a straightforward calculation indicating that 50 days of such sustained acceleration could result in a velocity change of 86 meters per second. The arithmetic is factually correct, and the underlying data are indeed real. However, the extrapolation, the leap from the existence of an acceleration to the conclusion of an Earth-targeting maneuver, relies on assumptions that we are currently unable to verify. For such an interception to occur, the acceleration would need to be sustained, precisely directed, and perfectly synchronized with Earth's orbital position at the exact opportune moment. None of these critical conditions have been established. We have thoroughly examined the predicted trajectory and missed distance. Official sources indicate that 3I Atlas will pass Earth at an approximate distance of 1.88 astronomical units, equivalent to about 270 million kilometers, on December the 19th, 2025. This distance is exceptionally large. To achieve an intercept from this distance would necessitate a significantly greater velocity change, applied over a considerably longer duration, with meticulously precise timing. The available numerical data do not support the claim of an Earth intercept. We have diligently explored potential natural explanations for the observed acceleration. Outgassing, the sublimation of ices that generates propulsive thrust, remains the default hypothesis. However, the implied rate of mass loss is substantial, constituting at least 1/16 of the object's total mass over a single month. If Avi Loeb's calculations are accurate, this process should have resulted in a prominent coma, a phenomenon that telescopes have not definitively observed thus far. The scientific community awaits further conclusive evidence on this aspect. We have also considered more speculative, albeit intriguing, possibilities. Could 3I Atlas be an artificial construct, an interstellar probe dispatched by another civilization? Its peculiar acceleration, estimated size, and trajectory collectively raise pertinent questions. Nevertheless, there is currently no irrefutable evidence, no definitive techno-signature, no radio transmissions, no non-volatile thrust signatures to substantiate this hypothesis. It remains purely speculative, though undeniably captivating. The narrative that proliferated on social media amplified this claim, transforming a scientific anomaly into a sensationalized account of an alien interception. This narrative disseminated with far greater rapidity than the underlying scientific analysis, blurring the boundaries between empirical data and speculative interpretation. It serves as a potent reminder of information dissemination dynamics in the contemporary era, how uncertainty can morph into spectacle, and how pattern-seeking human minds can fill perceived gaps with dramatic conjecture. We have also considered the potential implications should the most dire scenario prove true. If the object were, through some improbable sequence of events, to intercept Earth, the consequences would undoubtedly be catastrophic, representing an extinction-level event. However, the chain of assumptions required to reach this conclusion is exceptionally long and inherently fragile. Such a scenario would necessitate capabilities, intentionality, and temporal alignment on the part of the object that verge on the implausible. We have also broadened our perspective, contextualizing 3I Atlas within the broader landscape of contemporary space science. Advancements in exoplanet atmosphere imaging, ongoing research into dark matter, The sophisticated capabilities of AI-driven orbit prediction and the evolving techniques in radio astronomy all contribute to a richer understanding of this particular object. This investigation transcends the mere study of a single celestial body. It delves into the very methodologies we employ to explore the universe, detect anomalies, interpret data, and prepare for the unexpected. Therefore, what are the principal takeaways from our comprehensive analysis? Firstly, 3I Atlas represents a rare and scientifically invaluable interstellar visitor, irrespective of whether its origin is natural or artificial. Secondly, the arithmetic underpinning the 86 meters per second velocity change calculation is accurate, but it does not inherently imply an impending Earth impact. Thirdly, several critical unknowns persist. The precise vector of the acceleration, its sustained duration, and its temporal alignment relative to Earth's orbital path. Fourthly, upcoming observations scheduled for late 2025 are of paramount importance. Data regarding mass loss, astrometric residuals, spectroscopy, and radio monitoring will collectively provide clarity on the object's true nature. Fifthly, while worst-case scenarios are undeniably dramatic, they are contingent upon numerous unverified assumptions, and official agencies have definitively stated there is no imminent threat. Sixthly, a confluence of broader scientific disciplines converges on 3I Atlas, rendering it a focal point for multiple lines of inquiry. Let us now address the projected timeline. The object's perihelion, its closest approach to the Sun, occurred around October the 30th. It has now passed this solar apogee and is proceeding outbound. November marks the commencement of intensified observation campaigns as the object emerges from the Sun's glare, becoming more amenable to observation. December the 19th, 2025, is the date of its closest approach to Earth, the very moment highlighted by the social media claims. By this date, we will have accumulated several weeks of additional observational data. Early 2026 will witness the object's outbound trajectory, potentially including a distant flyby of Jupiter around March. Following this, 3I Atlas will recede from view, venturing deeper into the outer solar system and eventually returning to interstellar space. What should you be looking for in the coming weeks and months? Monitor official orbit updates from NASA, the European Space Agency, and other prominent space agencies. Pay close attention to any refined calculations of the missed distance and any modifications to its predicted trajectory. Examine spectroscopy results closely. Are volatile compounds being detected? Is a coma forming? Does its observed color remain unusual? Review imaging reports from advanced telescopes like the Hubble Space Telescope or the James Webb Space Telescope. High-resolution photographs may reveal surface features, energetic jets, or other structural anomalies. Keep abreast of announcements from radio telescope facilities. Any detection of signals within the 1.4 GHz band or other frequencies would constitute a monumental development. Furthermore, observe the discernible contrast between media narratives and official scientific statements. How do mainstream news outlets present the story? Do they emphasize caution or sensationalism? How do scientists respond to the circulating social media claims? This dynamic interplay between public perception and scientific rigor is an integral aspect of this ongoing narrative. If no dramatic observations emerge by early 2026, what will be the implication? It will almost certainly indicate that the maneuver claim was unfounded. If the object behaves consistently with a comet, exhibiting predictable outgassing that diminishes as it moves away from the Sun, if its acceleration decreases or ceases, and if no radio signals are detected, then the natural explanation will prevail. In this scenario, 3I Atlas will join the ranks of other intriguing, yet ultimately conventional, interstellar visitors. However, should anomalies persist, if the acceleration continues unabated even far from the Sun, If mass loss is minimal despite observed thrust, or if radio signals are detected, then we will indeed be confronting a genuine enigma. At that juncture, the more speculative hypotheses will transition from conjecture to subjects demanding rigorous scientific investigation. Will 3i Atlas ultimately settle into the category of an interesting but natural celestial body, or will it become the first definitively confirmed engineered interstellar probe? The answer will not be found in social media speculation, but will emanate from the observations of telescopes, the analysis of meticulously gathered data, and the diligent efforts of scientists engaged in measurement, analysis, and interpretation. One final thought. The universe does not inherently cater to our comfort or anticipation. It operates according to its own fundamental principles, irrespective of whether we are prepared for its revelations. For centuries, humanity has been engaged in a gradual process of realizing that we are not uniquely central, nor are we alone in any absolute cosmic sense. Every significant scientific discovery has represented a step towards greater humility. 3i Atlas, regardless of its ultimate classification, represents another such step on this profound journey. If it is a comet, our understanding of the diversity of interstellar visitors will be enriched. If it proves to be something else entirely, it will underscore the possibility that the galaxy is far more intricate and perhaps more populated than we currently conceive. In either outcome, this celestial object serves as a powerful reminder to direct our gaze upward, to cultivate unwavering curiosity, to persistently question, and to remain open to possibilities yet unimagined. The investigation is far from complete. Indeed, it is merely embarking on its most critical phase. The coming months will be instrumental in determining whether the social media claims were merely flights of fancy or if something truly extraordinary is unfolding. By early 2026, we will have a clearer understanding. Until then, vigilant observation of the skies is paramount. The universe in its vastness is observing us in return.